Hello, it's Keith here, and this is lesson 5 of my Super H assembly programming tutorials. It's the final lesson, and so what we're going to do today is cover the remaining commands that we've not got to in any of the other parts. Now, some of these are still very important, so please stick around until the end. We're going to be looking at the final mathematic commands, shifting with carry to effectively combine two 32-bit values to make a 64-bit value for addition and subtraction. We're going to look at the concept of overflow, some other weird commands, multiplication and division, of course, which a lot of systems don't have, or the 8-bit systems I'm used to do not have, but this system does. And we're going to look at a few other weird commands that I never needed, and you may never need either, but for completeness we will discuss them. So let's get on with it. Let's finish the job of looking at Super H. Okay, so we are looking at lesson 5 today, and as always there's a jump block at the start. And so what we're going to do is we're going to look at add and sub carry. Now this, on the Super H, we use the T flag for our carry. Now we discussed the use of the T flag for carrying bits when we were doing bit shifts last time, but this time it's going to be for a digit that is passed out of an addition or subtraction function. So we're going to use the add C command, which adds and updates the T flag and uses the T flag as part of addition. So let's fire up our emulator and let's see what we got. Okay, so we're going to be using two 32-bit values, R0 and R1, as a 64-bit pair. Now, R0 being on the left is going to be the high part, and R1 is going to be the low part. And we've loaded this fairly high value into the low part, and this is 0 value into the high part. And then what we're going to do is we are going to have a second value, a second 64-bit value that we're going to add, and the low part of that is all threes, which means if we repeatedly add it, it's going to cause R1 to fill up, and then we're going to basically add the carry from the low part into the high part. Now, because we're using add C, we need to clear the T flag before we do the first addition. So we're clearing the T flag here. The first add C will effectively update the T flag with any carry caused by this first addition, and then that additional carry will be added to the second part here by that second command. So you can see here, we start with R0, A0 and R1 with that value there. We repeatedly add all those threes, and then once we go over EDCB A987, that causes a carry because it wraps back around to 20FEDCBA, and that carry is being effectively added to R0 by the second command here, the second add C here. The carry is being passed through in the T flag here. Now you can't see the T flag represented here because the T flag is actually being consumed by the command in the middle, so by the time we show our monitor it's too late, it's already gone. But you can see here that addition has indeed basically added to the second part. Now we have to, in this case, use two registers for our addition. One of the registers is just 0, but of course we could give it a different value here. We could just give it a simple value of 1 here. Let's make that a little bit clearer what we're doing here. So we could add a value of 1 as that high part, so just to show. So you can see here that it goes 1, 2, and then it jumps from 3 to 4 because the bottom part has overflowed. So we're effectively adding two 64-bit values together using the 32-bit registers of this processor. Now, for me, coming from the 8-bit world, it's fairly unlikely that I would ever work in 64 bits, but obviously there's definitely times you're going to need to work in 64 bits, and the Super H is an extremely powerful processor. It's a 32-bit processor. It was designed for 3D gaming and things, and there's no reason it couldn't be used for mathematical purposes like accounting. I'm not sure that it ever was, but it certainly would have been designed with that kind of capability. So it's going to want to be able to work in very high precisions for its addition and subtraction. Now we looked at add C for addition there. We can use sub C as well, and the T flag in this case acts as a carry. Now let's just restart that. Let's just get rid of my my extra 1 there just for clarity. So in this case we're doing the opposite, and now we're doing our subtractions here. And so we started with this value here, and after our last addition it ended up as 54320FEC, and then we are going to repeatedly subtract our test value in the same way as we added it. And so you can see here we are repeatedly subtracting, and then once this goes below 0 the T flag is set, and that is effectively subtracted from our 0. So the T flag is acting as a borrow on this system, and so that is continuing until finally we end up in exactly the same place as we started, which is exactly what you'd expect if you do a repeated set of additions and then subtractions. So there we go. Very straightforward if you need to do 64-bit addition and subtraction, to use sub C or add C to work with the carry. So that's how we can deal with with a value exceeding its limit with regards to addition and subtraction. But there is another kind of exceeding of limits that we might want to test for. This is referred to as overflow, and if you're anything like me, when I started learning assembly, I didn't really understand what that would mean, because it's like, well, we just saw the carry, that's overflow, the register has overflown, it's reached its maximum value and it's gone over the top. Isn't that overflow? Well, overflow means something slightly different in hexadecimal and with these assembly processors. Now, overflow refers to the signed numbers, you see, because if you think about it, when we've got a signed number, and if we just think of a very simple small 8-bit signed number, as an 8-bit signed number can go from -128 to +127. And of course, this will just have values from 0 to 255 in binary 0 to FF. Now, because this byte is only 8 bits, if we have a value of 127 as a signed number and we add 1, that will become 128. But the hexadecimal value of 128 is actually a negative number. So by adding 1, we've gone from a very large signed positive number to a very small signed negative number, and not intentionally. And that's what's referred to as overflow. It's not the changing of the sign, it's the unintentional changing of the sign. Because if we've got a value of 1 and we subtract 2, it will go to -1. That's not unintentional. But if we go from a value of -128 and we subtract 2, we will go to +126, and that was unintentional, and that's the overflow. It's the unintentional changing of the sign. So how do we detect it? Well, we need to use special commands. The regular commands do not set the T flag according to overflow. The T flag doesn't usually get set at all. It will get set by our add C and our sub C for the carry. But if we're concerned our value might overflow, we need to use add V and sub V, and these will set the T flag according to the overflow. So let's fire up this example and let's see if we can cause an overflow. So we've got this very high positive number here, and we're going to add the value 1 repeatedly to it. Now, when that top nibble turns to an 8, that's going to become a negative number. And because we're adding, that's not going to be intentional. We wouldn't expect to add a number to a high positive number and it to become negative, unless we're working in hexadecimal and we've had an overflow. So let's see what happens when we repeatedly add 1. Now, in this case, we are actually running our monitor immediately after the add V, so we will actually show the correct state of the T flag after our command has been executed. So we're repeatedly adding our 1. So you can see we've got 7 lots of FD, 7 lots of FE, and then 7 lots of Fs. And in all of those first 3 cases, the T flag was false. Now, when this wraps around to 8 and lots of zeros there, this has gone from a very high positive number to a very low negative number now. This is a very, very negative number here. And that wasn't intentional, was it? And so the T flag has been set there to true, because what is true is that the value has overflowed, and that's what add V does. It sets the T flag if an overflow occurred, in this case because a positive number changed to negative, and then we're repeatedly adding 1 again. And in this case, those are all fine, because there's no continuous overflow. It's sort of saying, well, it did overflow, but now these successive additions are all okay. So that's the addition, and we can do the same for subtraction. So now we're going to do the same with our subtraction. Now, we've got our negative number and we're repeatedly subtracting 1 here, but then we've got to the absolute limit of a negative number here with this 8,000. Of course, there's no overflow in any of those cases, so those are all fine. But once we subtract 1 again, we go from our very small low number to our very high positive number again. And so the T flag has been set again, because that is once again an overflow. It doesn't matter whether a positive incorrectly changes to a negative or a negative incorrectly changes to a positive. They're both an overflow. So that's why that has been done. But again, just to iterate, this is only if the sign changes unintentionally. So if I change this test value here to -3 and I run again, well, you can see here we've gone from Fs to lots of Fs and Fe, then FF, and then 0, 0. So this is -2, -1, 0, 1, 2 here. none of these have caused an overflow because the sign has changed, but it's changed entirely correctly because we would totally expect that. So again, overflow isn't the changing of a sign, it's the incorrect changing of a sign. And it might not be something you need, it depends what you're doing. Okay, next we're going to look at some commands that are quite handy for working with different parts of registers where you actually want to move bits of them around. Now, we're going to look at the commands known as swap and extract, so let's fire these up. So these are for cases where you've got data in your registers, but you need to move bits of them around. I mean, in a 16-bit word case, you might want to swap the endian, but also if you've got something in the high part you need to move to the low part, these could be handy to you. So we're going to load these test values into R0 and R1. And then the first command we're going to use is swap B, swap byte, and we're going to swap B R0 and store the result in R0 here. Now, R0 contained 0, 1, 2, 3, 4, 5, 6, 7. Now, we've worked at the byte level, and what this does is it swaps the 2 bytes in the 16-bit value in R0, so the top half is unchanged. But the 4, 5, 6, 7 has become 6, 7, 4, 5. So we've kind of swapped the endianness of that 16-bit value in a way. So that is what swap B does. Swap W actually swaps the two 16-bit words within the 32-bit value, effectively swapping the 2 halves. So we've got here FEDC BA98, but that becomes BA98 FEDC. So not swap the endian there, but we've swapped the 2 halves, and that could be handy for you if you're using a 32-bit register to store 2 different 16-bit values or something. Maybe there's a big case that you've done that, or maybe there's a case where you've, like I've used the example before, if you've loaded in a joystick's values, but the data's in the wrong place and you need to swap it to the opposite side. Saves a lot of bit shifting if you can do that. So that's those 2 options. And the other one is got a slightly surprising name and purpose. This is called extract, EXTRCT. Now this actually works with a 64-bit pair. So if we use R0 and R1 here, what this does is it uses R0 and R1 as a 64-bit pair, with R0 being the top half of the pair. So it takes the middle 32 bits from that 64-bit pair and it stores them in the right-hand register, so in R1 in this case. Well, what does that mean? Well, if we start with the value 1, 2, 3, 6, 7, 4, 5 and BA98 FEDC here in these 2 registers here, R1 will end up with the value 6745 BA98, and it's got that from the least significant 16 bits of R0 here, the top half, and the most significant bits of R1, the bottom half. So you can see there that we've ended up with 6745 BA98 there in R1. Strange command. I've never thought of a time that I would need to do that, but you know, as I say, if you were working with 64-bit values and you wanted to effect a divide, I mean, that could be handy. Or if, as I say, if you've got 2 registers with some kind of binary data like pixel data or something and you need to take a certain part of it, could be useful. Interesting command to have, so definitely worth bearing in mind. Another interesting command that's definitely worth bearing in mind is multiply. A lot of the old 8-bit systems don't have multiply, so I tend to get quite excited when I see a multiply command. I'm used to have to doing everything with bit shifting. Anyway, the Super H, like most 32-bit processors, does indeed have a multiply. However, there are a variety of different multiply commands for different multiply jobs. The other interesting thing about the Super H, and this is sort of a bit more common in the RISC world and things, is that we actually have some special registers. So when we perform a multiply, we don't get the result back in one of our registers, or one of our normal general purpose registers. They go into special registers, MAC-H and MAC-L. MAC-L is the low part for 32-bit results, and MAC-H is the high part for 64-bit results, and MAC-H and MAC-L combined, of course. So we may need to use those, and we can use the STS command to get the value from one of these special registers into one of our boring old normal registers. So that's what we can do. Now what we're going to do is we're going to perform a variety of commands, and so we're going to take the value F000100, that's a hexadecimal value of course, and we're effectively going to multiply that by 3. Now, the first command we're going to use is mulu, M-U-L-U. Now, this returns a 32-bit value from 2 16-bit parameters. So, what we're effectively going to do with these values is we're going to effectively calculate 3 times 100, because it's only going to look at the bottom 16 bits of R1 here, and it's going to store the result in MAC-L. So when we do this, this is an unsigned multiply, and so we get the value 1000 times 3, and the result is 3000 in R2 because we've moved it from MAC-L into R2 here. So that's an unsigned multiply. Now, of course, we can also do a signed multiply, and we can do a 16-bit times 16-bit value, giving a 32-bit signed result with mols, if you will. And so what we've got here is the value minus 3 in R0, and we've got our same 1000 effective value in R1. Again, the top F is ignored because it's being treated as a 16-bit value here. And so we've basically got our minus 3 in R0 here. We've got our 1000 here. And when we've done that multiplication, you can see we get quadruple FD here, and that is effectively multiplying that by that 1000 there. So that is a correct signed result. And of course, if we tried to do that with our unsigned command, we would get the wrong value. If I just try that here, you can see we've got the wrong value there. The top bit is set to 0 there, which is certainly not correct. That is not the correct value if we wanted a negative number. So that is how we can work with two 16-bit values to get a 32-bit result. There is another option, which is just the mul command. Now this actually uses two 32-bit values and gives a 32-bit result, and within limitations this can actually work with signed or unsigned numbers. The limitation being is, of course, if the multiply causes an overflow and some of the precision is lost, because there's a limit to what we can represent in signed and unsigned numbers. Because if we multiply our unsigned number and the top bit gets set to 1, it will effectively have overflowed, so that could cause us some problems. So here what we're doing here is we're taking this test 32-bit value here. We've got our test value of minus 3 here, and you can see we've taken our value here, we've multiplied by this value here, and the result is being returned in R2 again because we've moved it using STS MAC-L with R2 here. And so that's trying it out with a signed number. We can also, of course, just use a positive number. That will just work fine as well, give a clearer result possibly. You can see there we've effectively done the multiply there. So that is using two 32-bit sources and a 32-bit result. But what about if we want more? What if 32 bits is not enough for us? Well, we can do do what's referred to as double multiplication for unsigned or signed numbers. We're going to use DMULU, and we're working with 32-bit values here, so we're specifying long here. And this will multiply R0 and R1, storing the result in MAC-H and MAC-L. So this is going to multiply an unsigned 32-bit pair and give a 64-bit result. Here's our 32-bit pair, and here's our other 32-bit pair, and we're going to move our 64-bit result back into R0 and R1. So let's fire this up and let's see what happens. So here is our value that we're multiplying by this, and when we get our result, it will be in this 64-bit pair here. And so that does look like it's given the correct value, so that has worked correctly. Now we can do the same for a signed number. We just use a different command, very straightforward. Here's our signed number, and we are doing our multiplication here of this negative number by this number here, and you can see that the sign has been passed across into the 64-bit value. The sign has been correctly represented there. So these are 64-bit calculations for 64-bit multiplication. These are for 32-bit, but as I say, if you're used to the 8-bit world like me, you're probably used to just using the shift commands like last time, and as I said before, they will effectively double and halve values. One thing that's worth bearing in mind is to my knowledge, all systems, they are actually, if you're just trying to multiply by 2, doing a bit shift is faster than using these multiply commands. So, but if you're trying to do multiplying by 35, maybe they're faster than doing repeated bit shifts and additions, which is what you have to do in the 8-bit world. Now that's straightforward multiplication, very nice there, but the Super H takes full advantage of its spare MAC-H and MAC-L registers. We have these commands known as multiply and accumulate. Now what these do is these actually allow you to perform a repeated set of multiplications and add the values to a build-up value that you can then read back later. So basically what we're going to do here is we've got two sources of test data that I just showed you, and we're going to load those addresses of those test data into R3 and R4. We're then going to clear the MacH and MacL. We have to do this with this special clear Mac command, because these commands we're going to use, this Mac command, it adds the result to those MacH and MacL, so we need to zero them first, and that's what we're doing here. We're just moving them to R0 and R1 just so that we can prove the point that they've been cleared. You can see here at the start they've been cleared to 0. We're then going to perform 3 iterations of the Mac command, and this is the syntax of the Mac command. So what this is going to do is it's going to take a 16-bit value from the address in R3, it's going to increment R3, it's going to take a 16-bit value from the address in R4, and it's going to increment R4. It's going to multiply those two together, and it's going to add the result to MacH and MacL. And so it's working in 32 bits. But MacH is actually, it's not a 64-bit command, but it is taking any carry from MacL as these repeated additions are being performed. So let's see what happened. Well, here are our test values here. And so basically what we're going to do is we're going to add, multiply by 1, multiply by 1 0, and then 1 triple 0 here. And so hopefully we'll be able to see pretty clearly the results. We're actually going to move from MacH and MacL after each iteration into R0 and R1. So after the first iteration, we've got the value 3 moved into R0 and R1. So that's been taken from MacH and MacL. Now, after the second iteration, where we were multiplying 1 0 by 4, we've now got 4 3, because the 4 0, as a result of that second multiplication, has been added to the original value in MacH and MacL of 3. So we've got 4 3. We're then doing a multiplication of 1 0 by 1 0, and so the resulting value in R0 and R1, and of course MacH and MacL by definition, is 1 0 4 3. Of course, we're only seeing those in R0 and R1 because we're repeatedly performing these move commands. If we didn't do that, the values would just be building up fine in MacH and MacL. I'm only transferring them after each iteration of this loop to show what's actually happening. So that is Mac. That was working with two 16-bit values and storing a result that is sort of 64-bit. A carry will be added to MacH, but it's not a true 64-bit command. But we do have a alternative of mac.l, which works almost the same, but this will use two 32-bit values and it will store a 64-bit result. And so we're doing the exact same thing here, this time with these 32-bit values. So you can see we've got R0 and R1 again with values of 0, and we're repeatedly running, and we've got effectively the same kind of result, just shifted along, because we've used the same kind of values, just shifted along. And you can see there that we have indeed multiplied 32-bit numbers to get a 64-bit pair. Very handy commands if you're doing repeated calculations, but you don't need the values in the in-between stages. And of course, if you're reading from memory, those only work reading from memory, but very handy commands there, definitely worth bearing in mind. We're now going to get on to divide, and divide is a bit of a shock to me. As I say, I'm not used to having multiplication and divide commands coming from 8-bit. So usually when I have a multiply command, I usually have a divide command, and we sort of have a divide command, but it's a bit odd. Basically, we have some divide helper commands. We don't have divide commands, we have divide helper commands. So these commands, div ou in this case here, div and div1, these do part of the job of division, but not all of it. We actually have to combine them with a whole bunch of other commands. Div0 is basically kind of a prep command, and div1 is actually the dirty work command. But basically, we can't use these on their own, and we have to do a sequence of other commands. And I'll be honest, I've done division and multiplication using bit shifting in 8-bit, but I didn't understand these commands. I've copied these straight out of the official SuperH documentation. They appear to work, but I'm not going to attempt to tell you how they work because I don't want to give myself a migraine trying to work it out. We're just going to discuss that they do work, and you can copy them like I did from the official documentation or from here if you want to use them. You can do division. It's not as convenient as we'd like, but it works. So let's try it out. Anyway, let's fire it up and let's see what happens. So we've got this value in R1 here and this value in R0. And what we're going to do is we're going to effectively divide a 32-bit value in R1 by a 16-bit value in R0. And we're going to give a result, and this is an unsigned command sequence here. So we're taking this value here, dividing effectively by 3. And it's all of these commands we have to do. We have to do all of them to get the right values. This is calculating the divisor here. And basically, it gives apparently the right result. It seems to work. So we've got this value 3322. We've divided by 3. So let's just check our calculations here. If I just get the calculator up here and we do the values, and we do the value 3322 divided by 3, we should get the value 110b. And you can see here we've got the value 110b. So that does seem to have worked. Now that's dividing a 32-bit value by a 16-bit value and getting a 16-bit result. If we use this sequence, we can divide a 64-bit value by a 32-bit value and get a 32-bit result, again unsigned. So this is effectively going to divide 3003322 by 300 here, and the result will be stored in R2 as a 32-bit value. So we've got our value here, 3003322 here, and we're going to have to use the Windows calculator because it seems my calculator can't deal with the 64-bit values here. So we've got this value of 3003322, and then if we divide this by 300, we should get the value 10011. And after our division, as a result of all of these commands, we've got 10011. So that division has indeed worked. So that's another option, 64 bits divided by 32 bits, giving a 32-bit unsigned result. Here we've done the same with signed values. We've got a 16-bit signed value and divided by a 16-bit signed value, giving a 16-bit result here. And we've performed that calculation here. That's been done there. And then we've also got an option for a 32-bit signed number divided by a 32-bit signed number, giving a 32-bit signed result. Again, very complex sets of commands here, but you know, if you need to do these calculations, it's going to be faster than anything else. But this div0 and div1 command, they're helping out, but they're not doing a whole lot of the work, not compared to some systems which do have a dedicated divide command. But anyway, as I say, if you need to do those calculations and you can't do them with simple bit shifts, they're there for you to use. The final commands we're going to look at in this tutorial series are just a few other commands that we're covering for completeness. I'm not sure you're going to need them, but I like to try and cover all of the commands that it's reasonable to do so. Some of these are known as test and set. Now, this is a bit of a weird command. What it does is it will test a byte at a memory address. It will see if it's 0 and it will set the T flag if it is. But what it will also do at the same time is it will set the top bit of the byte that was tested to 1. Now, why would you want to do that? Well, apparently it's designed for multi-CPU operations, so used for locking, in effect, that you're wanting to basically do something and you need to check if any of the CPUs doing it at the same time. Well, you're flagging that you want to try and use this resource, but you're also wanting to see if another CPU had already set that flag, and so that's, I think, what this is for. It could also be used for some kinds of peripheral maybe, but what we're going to do here is we've got a series of test values, 1s followed by 0s in bytes, and we're going to use test and set to test the two of those bytes. And because we're setting the top bit, the top nibble of 0 will go from a 0 to an 8, because the top bit set to 1 will be represented by an 8. So what we're doing here is we're using this test and set, and this is going to set the T flag to 1 if the byte that was tested had a value of 0. So in the first case, the value was originally a 1, so that was tested by this command here. Well, the value wasn't 0, so the T flag was cleared, so we've shown an F here as a result of our monitor. But then we've incremented the R0 and we've tested again. So this second byte has already also been tested, but that was a 0, and so in the second case, the T flag has been set. Now, you can see this has changed to 8180. It was 0100, but it's been tested and set, and the set has set that top nibble to 8. So that's what those have done. As I say, they may be commands you never actually need. Now, the next command you really probably won't ever need, not for the kind of programming I've been doing, but if you're doing sort of low-level programming, you might want the sleep command. This actually powers down the CPU until an interrupt. So if I run it here, we get absolutely nothing because basically there's no interrupts ever going to wake the CPU up. But this is designed for power saving, of course. You know, if you've got a device that's got external interrupts that could be fired, then you put your device to sleep, and then when the user presses a button to wake it up again, or when a piece of hardware calls for the CPU to do some work to it for it, then it will wake up, then you do the job, sleep it again, and save some power. But in our case, we don't need it. The final thing we're going to look at is some traps. Now, this is going to be the kind of thing that only works on certain CPUs. This will work on the 32X. It will not work on the Saturn, because what we're going to do is we're going to alter the VBR. We're going to create our own vectors and our own test traps effectively. Now, the vector base register points to a set of vectors. Vectors are just snazzy names for addresses. So we've got some addresses here. For the first address is just 0, so that's nothing of interest to us. But vector 1 is a pointer to my vector 1, this subroutine here. And vector 2 is this second one here. Now these will, because we've pointed the vector base to here, these will take the trap number of trap 1 and trap 2. So that's why I've called them my vector 1 and my vector 2. And so because we've changed the vector base register, we can now cause a trap to trap 1 and trap 2 with the trap A command, and this will execute one of these traps that effectively calls one of our subroutines. Now, in the case here, we've called trap 1, which runs this subroutine and just shows a T to the screen. We need to return with RTE to return from exception. This basically pops the program counter and the system register containing the flags off the stack. So this is restoring things for effectively like an interrupt. But in this case, no, it's not, that says vector 1, it should say vector 2. But in this case, we're just running our test code. But this wouldn't be usually how you would use this, and that's probably why the Saturn's getting quite angry. But if we create our own vectors, we can just use them like subroutines. But in other cases, you might want to call operating system calls, or you might use these to deal with problems. Maybe you call one of these in the case of a bug in your code. You know, maybe you've tried to do a division and you've been given a value of 0. You might want to call a trap that warns the user of that, so that the user knows there's a problem in the code. In other cases, traps could be used for things like debuggers and monitors and things like that. So, but as I say, in our case, we've just used a test one just so we can see the function of these trap commands. But again, to what extent they're useful to you will depend on the hardware you are actually programming. They might be completely useless to you. You may not be able to use them at all, just depending on whether you can alter that VBR register. Anyway, that's all we're covering for the Super H Basics series. So I hope you've enjoyed what you've seen. As I said before, go to the website, download the source code, the build scripts, try it all out. You're not going to learn everything just by watching these videos. But if you liked what you've seen, please stick around. Make sure you like and subscribe, because we're going to do some basic tutorials covering the programming examples that I've used to actually create this series, drawing the graphics to the screen and things. So we're going to look at the 32X and the Saturn a little bit, so that you can actually see, how I managed to do what I've done for these tutorials. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching. Goodbye.